Hello everyone. Can anyone confirm if I am audible as well as my screen is visible?
Yes, ma'am, you're audible as well as the screen is visible.
Yeah, thank you. Welcome to the first problem solving session of this deep learning course. So, I am Tanuka Bhattacharjee from ISC Bangalore. In these problem solving sessions, we'll do problems related to this week's or the some weeks course content. So, today we will focus on feature descriptors as well as the Bayesian classifier. So, we will these sessions will help you to get a deeper understanding of the concepts as well as it will help you to solve your assignments also. So, it will be a 2 hours session from 2 to 6. So, first 1 hour I will be solving some problems for you. For the second hour we will take questions. So, the session will be open till 6. You are open to any, we are open to any questions. So, let us start with the first problem for today. So, we have seen in the first week about descriptors of shape as well as region of different objects. So, the first question is related to those shape descriptors or boundary descriptors. So, the question is the signature descriptor of an unknown shape is given in this figure and we need to identify the unknown shape. So, as we know what is a signature descriptor. So, if you are given let us say a unknown shape like this, if you are given unknown shape like this, you have to first take the centroid of this shape and you have to take a reference direction. Let us say I take the horizontal direction as the reference direction. Now, for each point on the boundary, if I join this centroid and the boundary point, then the angle that it makes is the theta angle, and this distance let us say we write as d theta or L theta, anything. Now, if we plot theta versus d theta, that graph will give us the signature descriptor. So, theta from 0 to 360 degree, we have to plot these distances of the boundary points from the centroid to get our signature descriptor. So, here one such signature descriptor is given, which is a straight line throughout. So, the value is distance of all the points on the boundary is constant from the centroid. We need to identify the unknown shape. I have a question. So, Shashi, as I explained, so signature descriptor is basically a boundary descriptor or boundary feature for any object. So, let us say you have this type of arbitrary shaped object as I have drawn here. Let us say this is your object and you want to obtain the signature descriptor for this particular shape. So, what you need to do for that, it is basically it is a way of expressing your boundary. So, some way of encoding the boundary characteristics. So, for that how we calculate this is we take the centroid of this object and we take a reference direction and we calculate two things. One is let us say we take a point on the boundary, we take the distance of that point from the centroid as well as the angle theta that it is making with the reference direction. Now, if you plot this theta in the x axis and the distance d theta in the y axis and form a graph, so that is the signature descriptor you get. So, basically it will depending on what is the shape of your object, how is the boundary, this shape descriptor will change. So, based on by looking at the shape descriptor itself, you can say what is the shape of this particular object. You do not need to know the entire boundary. Sorry, just a minute. So, that object can have many dimensions. So, how can we apply this angle thing as a general rule? So, if you are considering a 3D object, let us say you can so when we are looking at this boundary, I am not sure how to deal with it in general, but maybe when you are we can always have a projection of the object from top plane or in the side plane, and we can see the boundary of that particular projection, and we can obtain this feature from there. So, that way you can deal with a general case. You just take the top projection and treat it like a projection on a plane, and you get the boundary from there, and from there you compute it. So, based on which way you are taking the projection, this descriptor might change. So, that will also give a variation of the features. So, does that answer your question, Sashi? Yeah, okay. So, yeah, can someone tell me what is the shape that this feature corresponds to? Yeah, circle is the correct answer. So, all the points are equidistant from the centroid. So, that is how circle looks like. So, the first question answer would be circle. Now, let us look at one more such descriptor. So, this is one more signature descriptor of a shape. So, which option do you think this is? Circle, square, rectangle or equilateral triangle? Anju is saying circle. Okay, anyone else? Anju is saying square, sorry. Shashi is saying equilateral triangle. Okay, I am getting a lot of options. Yeah, most of you are saying this is rectangle, and that is the correct answer. So, it is not square or equilateral triangle, it will be rectangle. So, to explain that, let me tell you. So, let us say this is the rectangle, and we take the centroid over here, and we take the reference direction like this, and so this is our reference direction. So, when we are at theta 0, let us say this is some distance is there. Now, when you are increasing the theta value, the distance is increasing till this point.
Excuse me, ma'am, will you provide us the recording?
Yeah, the recordings will be uploaded and you will get the YouTube links for it.
Okay, yeah, thank you.
So, as I was saying, once you from the reference direction theta equal to 0, there is, let us say this is the distance. Now, once you are increasing theta till 45 degree, the distance is increasing. So, it is going up. Now, again the distance starts decreasing when you increase theta more towards 90. This is the minimum distance, and this distance is less than the distance at theta equal to 0 degree. So, if it was a square, this two distances at 0 and 90 would have been same. So, your signature would have dropped till this point if it was a square figure, but since it is a rectangle, it has dropped further, it has dropped till this point. Now, again after that, again you keep on increasing the theta value, your distance keeps on increasing. This is for the longer side, this part, and for the shorter side you get this part. So, the distance is more when you are considering, let us say this thing or this thing, the distance is more. So, you get this shorter semicircles, and when you are considering the longer side, you are getting this longer portions. So, this corresponds to a rectangle. So, if you have a square for say example, then it will look something like this. Something like this. Similarly, if let us say we have a equilateral triangle, let us say we have a equilateral triangle. So, here is the centroid, and let us say I take the reference direction along the perpendicular. along the perpendicular. So, here this side is theta, this side is d theta. So, initially there is certain distance, let us say at 0 degree, then the distance starts increasing till this point, again it decreases, comes to the initial level here and again increases, like that it goes. So, it will decrease, increase, then decrease, so something like this you will get. So, there are mostly 3 such complete arcs are there in case of equilateral triangle, whereas in case of square it was 4 arcs and all are symmetric. For rectangle those are not symmetric. So, this is about the signature descriptor, which is one type of a shape feature or boundary feature. Now, another type that we have read about is the polygonal descriptor. Safiq, the rotation we generally take anti-clockwise, but that is the convention that you should take. Whatever convention you are taking, you should always maintain that when you are going for any, let us say building some classifier and you want to have the feature as a signature descriptor, you should have a same convention throughout, but generally we take the anti-clockwise direction. Okay. The next thing we have is the polygonal descriptor. So, the question was for a polygonal descriptor, to obtain a polygonal descriptor using splitting technique, which should be the starting guess. Okay, so Sashi is saying ki there is no constant distance, so it is not a circle, correct. It can't be a square because then curves should have same variations due to same sizes, correct. It is a rectangle because there is a pattern wise alternate for like length and breadth. Yeah, right. Can we analyze like this? Yeah, sure, you have got the point, correct. Any other question? Okay, then let us move on to the next part, which is the splitting technique wise polygonal descriptor. Yeah, the option was correct. Who said this? I forgot. Srividya Srinivasan. Yeah, your option is correct. So, let me just summarize the process of getting this polygonal descriptor. So, what we do is, let us say this is the shape we have. So, the initial points, as all of you are saying, we will take the 2 farthest points. Let us say these 2 points we will take as our initial guesses on the boundary. What we need to do is, first we join these 2 points. Now, the initial complete boundary is now splitted into 2 parts. So, first we let us say take the first part, and for each point on this boundary you will have to compute the perpendicular distance of that point from this the line joining the initial 2 points. Now, the point having the highest distance with highest perpendicular distance with this line, we will take that as the next point, and we will join these 2 and these 2. Similarly, you will have to do it for this half also. Let us say this one. Now, your boundary is again splitted to more number of segments. So, this is one segment, this is one segment, this part is another segment, this part is another segment. So, you keep on doing this process. In each segment, you take all the boundary points, take the perpendicular distance to the line, to the nearest line mostly, and you take the point with the highest distance from the line and take as that your next selected point, and you join with that the two boundaries, let us say these two we join next. Now, how long you will keep on doing this? As long as the distance, the maximum distance that you are getting from the line is above a threshold. Once you go below that threshold, you stop splitting that boundary anymore. So, like that you can have a polygonal approximation of any arbitrary shape. So, once you have a polygonal approximation, you can then derive any geometric features based on the geometry of polygons. So, these are two main shape descriptors that we have learnt in this course. The another thing that we have learnt is the region descriptors, which can be intensity, color or texture. Intensity and color are mostly the histogram based features. So, that is quite straightforward, but for the texture we have seen that we can use the gray co-occurrence matrix. So, let us say this is an example gray co-occurrence matrix of an unknown image. So, the different features you can compute from this particular matrix. So, the first one we have to compute is the maximum probability descriptor. So, here I must mention that this is the gray co-occurrence matrix before normalization. So, as we know, all the definitions of the properties are based on the normalized matrix. So, we have to normalize this matrix first, then you do the feature computation. So, the first feature is the maximum probability descriptor. First one is the maximum probability descriptor. For that, what we do is max over ij, Cij, where Cij is the ijth element of this particular matrix, that is the ith row jth column element of this matrix in a normalized form. So, here to normalize you will have to sum all the entries, and if you sum this entries here, the sum will amount to 17. Here sum equal to 17. So, if you want to take the maximum, as you can see this is 3 in this particular matrix. So, if we want to take the maximum probability descriptor, that will be 3 by 17. So, you just take the maximum element in the matrix and normalize it by the sum of the matrix to get the maximum probability descriptor. Now, second feature that we can compute is the element difference moment of order 1. So, the formula for this particular feature, I am writing it as EDM1, that is equal to summation over all I, summation over all j, I minus j to the power k into Cij, where you have to put k equal to 1 for order 1, right. Yeah. So, you can simply, we can compute this for one example. So, if you compute this for all the this is just I minus j to the power 1. So, it becomes just I minus j. So, all the diagonal entries will not have any contribution, only we will have to consider the other entries. So, if we just write it like this, if we just write down all the terms that we will be summing up. So, we will get minus 1 into 2 by 17, which is for this entry goes to 0 because I minus j is 0. Here I minus j is minus 1. So, minus 1 into 2 by 17, which is Cij for this particular element, plus next one is minus 2 into 2 by 17, plus if you see this one, this is the second row first column. So, the difference is 1. So, it will be just 2 by 17. This one does not have any contribution. The next one will be minus 1 into 2 by 17. Similarly, yeah, so this one is difference, this is third row first column. So, the difference is 2 into 2 by 17 plus 1 into 3 by 17. Again the last element has no contribution. You can simply sum this up to get the final value, and that will be 1 by 17. So, this is the element difference moment of order 1. Similarly, you can compute element difference moments of higher order, where you will just have k equal to 2, 3 like that. Now, the next one is inverse element difference moment. This is also same, just the formula is slightly different. So, I will just write down the formula for this. So, inverse element difference moment of order 1, that will again be summation over I summation over j C I j divided by I minus j to the power k. Here order 1, so you will take k equal to 1, and here you will have to take only those elements for which I not equal to j. Pranshul, okay, just let me go through the comments one. Pranshul Atri, why diagonal elements won't have any contribution? So, Pranshul, if you see the formula has I minus j to the power k. Here I am taking k equal to 1. So, for the diagonal elements, your I, j are always equal. So, it is either the, so this element is the 1, 1 element, this is the 2, 2 element. So, I and j are always equal. So, if I are taking the difference here, it will always be 0. So, those elements will never contribute into this. Vigneshwaran, Cij is basically the normalized values of this matrix. So, you will have to compute, so the entry of this matrix, let us say the first entry is 1, but while computing these features we take the normalized matrix. So, you will have to divide each element by the sum of all elements of this matrix. So, if you sum up all the elements here, that is 17. So, each element I am dividing by the sum to get the normalized matrix. Cij denotes that normalized elements. Yeah. Okay. So, similarly, we can compute the inverse element difference moment. Let me just take this down. 1, 2, 2. So, this was the matrix. Can anyone compute and tell me the answer for this? I am also computing in the meantime. Let me just do one thing. I will take the 1 by 17 common and I will do this way. Sharan, yeah, I will just complete this one and I will explain the second one again. So, it should be 1 by 17 it seems. Yeah, right, it should be 1 by 17. Shafiq, it is not 3 by 17, it should be 1 by 17. Someone was asking about the part 2. Sharon, you were asking about the part 2, which is the element difference moment. So this is the formula for element difference moment. So we first compute the Gray co-occurrence matrix, which is already given to you in this question. This matrix is the Gray co-occurrence matrix. So we will have to, this matrix is in the original form. You will have to take normalized matrix in order to compute all these features. So how do you normalize? You just divide each element by the sum of all elements in this matrix. So here if you sum it up, all the elements, you will get 17. So I am just getting the normalized matrix as dividing each element by 17. So your normalized matrix is something like 1 by 17, 2 by 17, 2 by 17, then 2 by 17, 1 by 17, 2 by 17, then 2 by 17, 3 by 17, 2 by 17. This is basically your normalized matrix that you should consider for obtaining these features. This Cij is the element of this normalized matrix, ijth element, ith row, jth column. So if you simply put the values in this particular formula, so you don't need to consider the diagonal elements because I equal to j for them. So those will amount to 0. For the remaining, if you just take I minus j, for example, for the first element this is 1 1, so this is 0, I minus j is 0. For the second element this is, it should be 1 2, not. So second element ij index is 1 2, so I minus j will be 1, minus 1. So you have minus 1 into the element is 2 by 17. Like that, the third element, the ij is 1 3. So I minus j is minus 2 into 2 by 17. Similarly, you should put for all the elements and simplify. That will give you the value. Does that clear the doubt, Sharon? These two features are quite similar, the element difference moment and inverse element difference moment. They are computed in the similar fashion. And last feature that is remaining is the uniformity. So uniformity is simply the sum of square of all the elements. So uniformity is basically summation over I summation over j Cij square. So this will also you will have to consider the normalized matrix as before. So Vigneshwaran, you have written 35, but actually you will have to consider the normalized matrix. So it will be 35 divided by 17 square. So every element you should consider as the normalized matrix, because all the definitions are given as in terms of Cij's, where Cij is the normalized Gray co-occurrence matrix. Okay. So I guess the concept of this feature extraction from Gray co-occurrence matrix is clear to anyone. If you have any doubts, you can just post it in the chat. I'll wait for 2 minutes here if you have any questions. Now let us move on to the next topic. So this was about the feature descriptors, shape descriptors as well as region descriptors. Now we will move on to the Bayesian classifier. So as you know, first we will talk about the Bayesian minimum error classifier. So Bayesian minimum error classifier, what does it say? Let's say you have a feature vector x and you have two classes omega 1 and omega 2. In that case, P omega 1 given x, this gives you the a posteriori probability of the class omega 1 given the feature vector x. So, according to Bayes minimum error classifier, if you have the a posteriori probability of class omega 1 is greater than the a posteriori probability of class omega 2, then you assign the feature vector to class omega 1. Whichever class has higher a posteriori probability, you assign your feature vector to that particular class. So, this is called, why this is called minimum error classifier, because when you are classifying x as omega 1 as a element of omega 1, because you have higher a posteriori probability of class omega 1 given the feature vector x, but then also there can be some feature values for which the probability of class omega 2 is also not 0. So, given x, the probability of class omega 2, the a posteriori probability of class omega 2 is also non-zero. So, there is a chance of error there, but that is the minimum. So, this is the minimum between the two. So, this is the error. So, the chance that you have that this feature belongs actually to omega 2, but you are classifying it to omega 1, this is this probability, and this probability is minimum in this case. So, this is called the minimum error classifier, that because the error probability is minimum. Now, here the question is, this is a two class problem, let us say class omega 1 and omega 2. And the posteriori probability distribution, this omega 1 given x and omega 2 given x are given here. So, the two are these two, this is for probability of omega 1 given x and this is for omega 2 given x, this is the two a posteriori probability. Now, the unknown feature vector is here, x1 is your unknown feature vector, you need to classify it based on the Bayes minimum error classifier. So, you can see this. So, if you first consider the first class omega 1, so this is the value for probability of omega 1 given x equal to x1. So, given your feature vector x is x1, value is x1, the probability of class omega 1 is this much, and this is the probability of class omega 2 given x equal to x1. So, among these two we easily see that probability of class omega 1 is higher, the a posteriori probability is higher for class omega 1. So, based on Bayes minimum error classifier rule, we will assign this particular feature vector x1 to the class omega 1. So, the answer was correct by Pranshul, it is option A, x1 is an element of class omega 1. I hope the concept is clear to everyone. So, you just need to, for any unknown feature vector, you just need to compute the a posteriori probability of both the classes given that feature vector, and whichever class has the higher a posteriori probability, you will assign the feature vector to that particular class. Now, here all these a posteriori probabilities are given to you, but in the next problem we will try to see some of these probability concepts, how to compute them. So, here what is given is, let us say x is a discrete single dimensional feature. This is computed from objects belonging to two classes C1 and C2, and x can take values like 2, 4, 6, 20. So, every even value from 2 to 20, that is the possible values for x, and x can come from two classes C1 and C2. The class conditional densities, the class conditional probabilities for both the classes are shown in the figure. So, this histogram gives you the class conditional density. So, class conditional density means given the class, let us say you are considering class C1, what is the probability density of the feature vector x? Feature here it is just a single dimensional feature, so the feature value x. So, you just compute the probability density of your feature considering only elements of class C1. Whatever you get, that is the class conditional probability for class C1. So, here this blue histogram basically gives the class conditional probability of class C1. Similarly, red is for C2. Now, it is mentioned that during data collection we observed that 1000 out of 5000 objects belong to class C1 and rest belong to class C2. Now, given these observations, first you will have to compute the prior probabilities, probability of C1 and probability of C2. So, this is the easiest one. Prior probability means just the probability of occurrence of class C1 and class C2. So, here it is mentioned that when the data was collected, it was observed that 1000 out of 5000 belong to class C1. So, if you want to compute the probability of class C1, that is just 1000 by 5000, which will be 0.2. So, this is the prior probability is just the probability of occurrence of that particular class. So, you just considered 5000 samples and 1000 were favorable. So, you just get the probability as 1000 by 5000, 0.2. Similarly, for the other class you can compute, that will be all the rest are belonging to class 2. So, 4000 by 5000, that will be 0.8. So, the sum will be 1 because it belongs to either of the two classes. Now, the next question is compute the posterior probabilities, probability of C1 given x equal to 8 and probability of C2 given x equal to 8. So, here the information that you have is the class conditional densities and you have the prior probabilities of each class. You need to compute the posterior probability. So, let us say the first posterior probability is probability of C1 given x equal to 8. So, according to Bayes rule, you can write it as probability of x equal to 8 given C1 into probability of C1 divided by probability of x equal to 8. This is just the normal Bayes rule. You can write the conditional density like this. Any conditional probability you can change like this. Now, here you already know the value of probability of x equal to 8 given C1, that is basically from this class conditional densities you will have to take the value at x equal to 8. So, you already have the curve, you just need to read the value at x equal to 8. Probability of C1 and C2 you have already computed. The only one remaining is probability of x equal to 8. If we compute that, so probability of x equal to 8, you can write it as probability of x equal to 8 given C1 into probability of C1 plus probability of x equal to 8 given C2 into probability of C2. You can split this probability like this, and if you put the values, what you will get is, so for class C1 the class conditional density is given by this blue histogram. So, the value at probability of x equal to 8 given C1, so that is this value, this is 0.45, and you have computed the probability of class C1 as 0.2. Similarly, from the class conditional density of class C2, which is the red histogram, you can compute this quantity, probability of x equal to 8 given class C2, which is this value, this is 0.05 into probability of C2 is 0.8. Right. If you compute this, this will be 0.13. Let me just check it once. So, we have computed probability of x equal to 8. Now, you can simply put the values in this equation to get the final posterior probability. So, this will be 0.45 into 0.2 divided by 0.13. So, finally, you will get 0.692. Yeah, right. Similarly, you can compute the posterior probability of C2 given x equal to 8, that will be probability of x equal to 8 given C2 into probability of C2 divided by probability of x equal to 8. So, 0.05 into 0.8 by 0.13. So, that will be 0.31. So, this is how you, given a data, real world data observations, this is how you compute the prior probabilities of each classes. Then once you have the class conditional densities from the observed data, using that as well as the prior probability, you can compute the posterior probability of each class at each value of the feature vector. This was about this probability calculations, and we already seen the Bayes minimum error classifier. Now, the more generalized form of that is the Bayes minimum risk classifier. So, the next question is on that, on the Bayes minimum risk classifier for two class classification. So, here, so I hope there is no question about the previous problem. Okay, let us move on to the next one. Yeah, thanks Pranshul. So, the next question is on Bayes minimum risk classifier. So, here we have been given the probability of classes omega 1 and omega 2. So, the prior probabilities, probability of omega 1 is 0.3, omega 2 is 0.7, that is given to you. Now, probability of x is also given to you, that is 0.545, and these are the class conditional density values. Given class omega 1, the probability of x is 0.65, given class omega 2, the probability of x is 0.5, and we have also been given the loss matrix values, which are in terms of lambda. Now, it has been mentioned here that the classifier assigns x to class omega 1, then which of the following is true? So, according to the Bayes minimum risk classifier, if your x is being assigned to class omega 1, that means the risk of, let us say we take the two actions alpha 1 and alpha 2 as x element of omega 1 and x element of omega 2. These are the two actions. So, if you are taking the first action, that is alpha 1, that means the risk of taking that action given your feature value x is less than taking the risk of taking the other action given your feature vector. So, if that is the condition, then according to Bayes minimum risk classifier, you take the action alpha 1, which is x element of omega 1. So, here you have taken this particular action ki the classifier has assigned x to class omega 1. So, this relation must hold in this case. So, we will have to compute these risks to get at the final inequality that we need to check. So, if you need to compute risk for any action alpha I given x, the formula is you have to take the loss of taking the action alpha I given the class is omega j into the posterior probability of class omega j given x, and you sum it up over all j. So, you compute the risk of taking the action alpha 1 given the class is omega 1 into probability of class omega 1 given x, plus you take the loss of taking the action alpha 1 given your class is omega 2 into probability of omega 2 given x. So, let us say first we compute the risk for class risk of action alpha 1 given x. So, that will be lambda alpha 1 omega 1 into probability of omega 1 given x plus lambda of alpha 1 omega 2 into probability of omega 2 given x. This we simply write as lambda 1 1. Now, Let's keep this as it is for now. Similarly, you can write the risk of taking the action alpha 2 given x. That will be this. So, according to our decision of the classifier, risk of taking alpha 1 action is less. So, R alpha 1 given x is less than R alpha 2 given x, because the classifier has assigned the element x to the class omega 1, that is, it has taken the action alpha 1 because it has less risk involved. So, if we simply do the algebra here, so let us take all of this in one side, and if I take probability of omega 1 given x common, that into lambda 2 1 minus lambda 1 1 plus probability of omega 2 given x common into lambda 2 2 minus lambda 1 2, that should be greater than 0. I have taken all of the elements to the right side. Now, we can write, because our question asked for the ratio lambda 2 1 minus lambda 1 1 divided by lambda 1 2 minus lambda 2 2. So, I will keep lambda 2 1 minus lambda 1 1 as the numerator. So, the required ratio lambda 2 1 minus lambda 1 1 by lambda 1 2 minus lambda 2 2 should be greater than probability of omega 2 given x divided by probability of omega 1 given x. So, we do not know the value of probability omega 2 given x or probability omega 1 given x. So, again we will have to simplify this posterior probability as product of class conditionals and the prior probability, because those informations are already with us here. So, we will write I have not written the denominator px in each of the cases, because those two cancels out if you have same x on both probability of omega 2 given x and omega 1 given x. So, the denominator in each case is px, that will cancel out. You will simply get probability of x given omega 2 into probability of omega 2 divided by probability of x given omega 1 into probability of omega 1. You can simply put the values over here. So, the values were the final value will be 1.79 and the answer is so lambda 21 minus lambda 11 by lambda 12 minus lambda 22 is greater than 1.79. In that case only your classifier will assign the feature vector x to class omega 1. So, this is how you compute for Bayes minimum risk classifier. Now, let us take one more example. This is about again the minimum risk classifier. So, here it is mentioned that consider a two class problem. Let us say again the classes are omega 1 and omega 2 with a single dimensional feature space, let us say x, and equal class prior probabilities. So, probability of omega 1 is equal to probability of omega 2. Now, let the class conditional densities be normal with distinct mean and variance. Let us say for class omega 1 we say the class conditional density is normal with mean mu 1 and standard deviation sigma 1 or variance sigma 1 square. Similarly, for omega 2 the mean is mu 2 and the variance is sigma 2 square. So, these are the class conditional densities are normal with these parameters. Also, you have been given the loss function. So, lambda 1 1 and lambda 2 2 are 0. So, if you correctly classify there is no loss, otherwise there are finite losses. So, lambda 1 2 and lambda 2 1 are positive. Now, you have to design the minimum risk classifier. So, to compute the minimum risk classifier, again we will have to compute the risk of the two actions, alpha 1 which is assigning x to class omega 1 and alpha 2 which is assigning x to class omega 2. So, I will simply write it down. This will be as I already we computed in the previous example. This is the expression for risk of taking the action alpha 1 given the vector x. Now, here you have been already given that lambda 1 1 is equal to 0. So, this first term accounts to 0. So, your risk of taking the action alpha 1 becomes lambda 1 2 into probability of omega 2 given x. Similarly, the risk of taking the action alpha 2 given x will be lambda 2 1 into probability of omega 1 given x plus lambda 2 2 into probability of omega 2 given x. Again, since lambda 2 2 is 0, this term will become 0. So, you will be left with only this term. Now, we need to design the classifier. You have both the risk values. So, according to the theory we know, we will assign the class the feature vector x to class omega 1, that is we will take the action alpha 1 if risk of taking the action alpha 1 given x is less than risk of taking the action alpha 2 given x. That means, what was the risk for taking the action alpha 1 given x? That was lambda 1 2 into probability of omega 2 given x. That should be less than lambda 2 1 into probability of omega 1 given x. Now, we have been given the information that the class conditional densities are normal. Currently, the expression is in terms of the posterior probabilities. So, we will have to go to the class conditional densities. So, we will write it as lambda 1 2 into probability of x given omega 2 into probability of omega 2 given divided by probability of x. This should be less than lambda 2 1 to probability of x given omega 1 into probability of omega 1 divided by probability of x. So, both side has your probability of x, which is a positive quantity. You can simply cancel this out. Also, it was mentioned in the question that both classes have equal prior probability. So, probability of omega 1 is also equal to probability of omega 2. So, these two also cancels out, only the remaining term is there. So, now we will put the expression of normal distribution into this. So, we assumed that for the class conditional density of class omega 2, the normal distribution is with mean mu 2 and variance sigma 2 square. So, the density function will be this is for the class conditional density of class omega 2. Similarly, for omega 1 it will be 1 by root over 2 pi sigma 1 square exponential of minus x minus mu 1 whole square divided by 2 sigma 1 square. This is with mean mu 1 and standard deviation sigma 1. So, here also these two cancels out, and now what we will do is we will take the log of this. So, if we take the log, this becomes log of lambda 1 2 plus log of 1 by sigma 2 minus, this is already exponential, we are taking the log. So, we will just get the exponent, that is this should be less than ln of lambda 2 1 plus ln of 1 by sigma 1 minus x minus mu 1 whole square by 2 sigma 1 square. Okay. You can simply take all the terms in one side and simplify it. So, that will become you can further simplify this by simplifying the square terms over here. Let's do that. Square mu 1 square minus 2 mu 1 x. This will also become x square plus mu 2 square minus 2 mu 2 x plus ln of lambda 1 2 sigma 1 by lambda 2 1 sigma 2 less than 0. So, as you can see, this is a quadratic equation. So, when you have this type of a condition, the classifier that we get is a quadratic classifier. So you can simplify it like, you take x square by 2 common, this becomes 1 by sigma 1 square by sigma 1 square minus 1 by sigma 2 square plus, if you take x common from these two terms, you get mu 2 by sigma 2 square minus mu 1 by sigma 1 square plus, finally you have half mu 1 square by sigma 1 square minus mu 2 square by sigma 2 square plus the log term, which is a constant quantity, less than 0. So this is the simplified expression for your classifier. This is the base minimum risk classifier for the situation where you have equal class prior probabilities and the class conditional densities are normal with different mean and variance, and the loss you are using is 0 if you correctly classify and some finite thing if you wrongly classify. Now here we have two special cases of this particular classifier. So first thing is, what will the classifier be if the two class conditional have equal variance, unequal mean, and lambda 1 2 equal to lambda 2 1. You can simply look at this. So you have equal variance. So you have sigma 1 equal to sigma 2, mu 2 mu 1 are different because you have different mean, and lambda 1 2 equal to lambda 2 1. If you simply put this, the square term goes away. So once you have equal variance for both the class conditionals, the classifier do not remain a quadratic classifier anymore, it becomes a linear classifier. So you just have x into mu 2 by, let us say I am denoting the common variance as sigma square. So sigma square by mu 1 by sigma square, sigma square plus half of mu 1 square by sigma square minus mu 2 square by sigma square. Here in the last log term, your sigma 1 sigma 2 are equal, lambda 1 2 lambda 2 1 are equal. So this ratio becomes 1, so log of that becomes 0. So this is the classifier that you have. So you have now you are left with a linear classifier. You can even simplify this expression, as you can see. So if we simplify this further, what we can get is x into mu 2 minus mu 1 should be less than so we will have half of mu 2 square minus mu 1 square. We are just cancelling out the sigma square from both sides. Now if you simply assume that mu 2 is greater than mu 1, that is mu 2 minus mu 1 is always positive. So whatever density has the higher mean, you take that as the class omega 2. So if you consider that, then this expression reduces to x less than half of mu 1 plus mu 2. So, this is the simple expression that you have got when we are imposing the constraint that both the classes have equal variance, as well as the loss for misclassification is same for misclassifying 1 as 2 or 2 as 1. So, your classifier just becomes a single linear classifier, where you will have to just check the value of x if it is below a threshold or not, and the threshold is just the average of the mean of the two class conditional densities. Now, another option that we had, option 2, that was the two class conditional densities have 0 mean, unequal variance and lambda 1 equal to lambda 2. If that is the case, so both mu 1 mu 2 are 0, sigma 1 sigma 2 are different, and lambda 1 2 equal to lambda 2 1. So, if you take this expression, this one, which was the final expression for the classifier. So, what you get is x square by 2 into 1 by sigma 1 square minus 1 by sigma 2 square, that is the first term is as it is. Now, your both means are 0. So, mu 1 mu 2 both are zeros. So, the second term goes away, the third term also goes away, and then in the last term lambda 1 2 and lambda 2 1 are equal. So, we are just left with ln of sigma 1 by sigma 2. Sigma 2 that should be less than 0. So, now if you have unequal variances, though your mean are equal, unequal variances leads to quadratic classifier, but when you had equal variances, you had a linear classifier. You can simplify this even further, and that will give you the final expression as let me write the 2 here, 2. So, this is the final expression that you will get. X square should be less than 2 into ln of sigma 2 by sigma 1 into sigma 1 square sigma 2 square by sigma 2 square minus sigma 1 square. This is the final classifier that you have got. So, any doubt about this one, you can post it now. Where will these recordings be available? So, you can check the course web page itself. So, I guess the authority will put up these links there. So, we will get YouTube links over there, as well as the slides also you will get access to it. Okay. So, now let us move on to the last problem of today's session. So, I will do this one and I will stop for any questions from your side. In the meantime also, if you have any question, you can ask it. So, in this problem, this is also a 2 class problem. The classes are, let us say, omega 0 and omega 1 with one dimensional feature space, let us say denoted by x. Let the class conditional densities be, probability of x given omega 0 is exponential, and probability of x given omega 1 is a uniform distribution 1 by 2a in the range minus a to a. The prior probabilities are equal. So, probability of omega 1 is equal to probability of omega 2. Assume we are using 0 1 loss. So, when you are correctly classifying you have no loss, when you are misclassifying you have 1 loss. Now, find the Bayes minimum risk classifier for this. So, as you know, if we have to make the Bayes minimum risk classifier, so we will take the action alpha 1, that is we will say that x belongs to, let us say, class omega 1, if risk of taking the action alpha 1 is less than the risk of taking the action alpha 0, which is here x belongs to class omega 0. Oh sorry, I have written omega 2 here, I am sorry. Now, as you know the expressions, we can simply put the values of this risks. So, this will be lambda 1 1 into probability of omega 1 given x plus lambda 1 0 into probability of omega 0 given x. Now, here you are already given the information that loss is 0 1 loss. So, your lambda 1 1 will be equal to 0 and lambda 1 0 will be equal to 1. So, if you put that, simply you are left with this term. So, this is your risk of taking the action alpha 1 given x. Let me just Similarly, the risk of taking the action omega alpha 0 given the feature vector x will be probability of class omega 1 given x. So, this reduces to your Bayes minimum error classifier, whichever class has higher posterior probability you are assigning to that class. So, now again you will have to go to the class conditional densities. If you go there, it becomes, the inequality becomes we simply cancel out px, and we were also given the condition that probability of omega 1 equal to probability of omega 0. So, these two also cancels out. So, the final expression you are left with is probability of x given omega 0 should be less than probability of x given omega 1 for assigning the element x to omega 1. So, basically it becomes at any point whichever class has higher class conditional density, you will assign the new item x, the test feature value, to that class, the one having the higher class conditional density. So, here the class conditional densities are also given, one is uniform density, another one is the exponential density. Exponential density. So, we can see the situation graphically. So, let us say this is your x. So, for class omega 0, the class conditional density is e to the power minus x for x greater than 0. So, this is something like this. This is probability of x given omega 0. And for probability of x given omega 1, this is 1 by 2a for x element of minus a to a. So, let us say this is something like this. Now, as I already derived, if you have probability of x given omega 0 is less than probability of x given omega 1, then you assign x to class omega 1. So, you see, if you consider this portion, let me use a different color. If you see this portion, both classes have 0 class conditional density here. So, we do not need to consider this portion. Now, for this next portion minus a to 0, the value of x from minus a to 0, here the class conditional density for class omega 0 is 0, whereas there is some finite class conditional density for class omega 1. So, always you can readily, always you will have probability of x given omega 1 is greater than probability of x given omega 0 for this region. So, this region we can always assign to class omega 1. Similarly, if you consider this region which is x greater than a, you see the probability of x given omega 1 is 0 here, and probability of x given omega 0 has some positive value. So, it will always be the case that probability of x given omega 0 is higher here. So, you can simply assign this portion to class omega 0 always. Now, the confusion remains for only this portion. Now, here there can be two cases. So, the maximum value of this probability of x given omega 0, that is e to the power minus x, the maximum value of this can be 1. When x is 0, this goes to minus 1. So, x is actually greater than 0. So, it never touches 1, but it asymptotically reaches 1. So, if it is the case that your probability of x given omega 1, which is the class conditional density of the other class, that is greater than 1, let us say. If this density is greater than 1, then what will be the situation? Now, we know that this class conditional density is given by 1 by 2a. Let us say that is greater than 1, or you can say a is less than half, less than half. If that is the case, then in this portion also you have probability of x given omega 1 is always greater than 1. So, in this portion also probability of x given omega 1 is always higher than probability of x given omega 0, because x given omega 0 can asymptotically reach the maximum of 1. So, always the class conditional density of class omega 1 is higher in this particular region. So, you can assign this region also to omega 1. So, there were two conditions. First condition that we considered is a less than half. In that case, what is you are assigning this also to omega 1. So, what is happening is, if your x is less than a or less than equal to a, then you are assigning x to class omega 1. If your x is greater than a, you are assigning x to class omega 0. This is the classifier if your a is less than half. Now, what is the case if a is greater than equal to half? So, these regions, this and this, remains the same, because there is no confusion here. Only confusion is with this region. Here what will happen is, you will assign to class omega 1, you will do this this decision if your probability of x given omega 1 is greater than probability of x given omega 2, omega 0. Now, if you put the expressions, because in this region that we are concerned with, here both are defined. So, you can simply put the expressions. Omega 1 is 1 by 2a, that should be greater than e to the power minus x, if you want to go with this decision that x element of omega 1. So, if you take the log of this, ln of 1 by 2a should be greater than minus x, or x should be greater than ln of 2a. If your x is greater than ln of 2a, then you are assigning it to class omega 1. So, here you are having a lot of conditions if your a is greater than equal to half. So, the first one is when your x is from minus infinity to minus a, you can put it anywhere, let us say put it at omega 1 to have a consistent decision throughout. Then from minus a to 0 you are putting at omega 1. Now, so when you have x less than equal to 0, or let us say when you have x less than 0, you are putting x to class omega 1. Now, let us say you have 0 to ln of 2a. ln of 2a. So, if x is greater than ln of 2a, this is sorry, did anyone say anything? No, I guess. Okay, fine. So, we saw that if in this particular region which we are now concerned with after 0, there if x is greater than ln of 2a, you will put it in class omega 1. So, when it is less than ln of 2a, you will put it in class omega 0. Now, when your x is greater than ln of 2a, take a x till the point a. Till the point a, you will put x in class omega 1. Lastly, when your x is greater than a, you put it in class omega 0. So, depending on whether your a is less than half or greater than equal to half, you have two different classifiers. Now, the second part of the question asked for the case when a equal to 0.25, find the probability of error. So, let us do that. So, we are given a equal to 0.25, which is less than half. So, what is our classifier? Our classifier is this one. So, if x is less than equal to 0.25, you assign it to class omega 1. If it is greater than 0.25, you assign it to class omega 0. So, x less than equal to 0.25, you assign x to class omega 1, x greater than 0.5, you assign it to class omega 0. Now, what is you have been asked is to compute the probability of error. So, what is the probability of error? The probability of error given your feature vector x is probability of class omega 0 given x when you have assigned x to class omega 1. So, if you have assigned x to class omega 1, the error that you can make is probability that x belongs to actually class omega 0. So, the probability of omega 0 given x, that is the probability of error when you are assigning to class omega 1. And if you are assigning to class omega 0, then the error is probability of omega 1 given x. Now, if you have been asked to compute the entire probability of error, that will be equal to integration minus infinity to infinity probability of error given x into px dx.
Good morning, madam.
Yeah, who is this?
No, madam, my children.
Oh, okay. Can you please put yourself on mute in that case? Yeah. So, you will have to
Tell madam fast.
compute this expression. So, now here, so you have two different expressions for probability of error given x. Yes, Sandeep, the recording will be provided, you will get a YouTube link for this. So, here when your x is less than 0.25, you are assigning it to class omega 1, and then your probability is probability of omega 0 given x, that is your probability of error. So, for minus infinity to 0.25, your probability of error given x is probability of omega 0 given x, then px dx, plus from 0.25 to infinity. So, in this region, if your x is greater than 0.25, you assign it to class omega 0, then your probability of error given x is basically probability of omega 1 given x. So, the expression reduces to this. Now, finally, so in this region minus infinity to 0.25, your probability of omega 0 given x, okay. First we will have to go to the class conditional densities, because we do not know the posterior probabilities. So, it will become right. So, now probability of x given omega 0 is your exponential curve. So, you can simply put that. I will put it in the next slide maybe. Now, you have been given the condition that you have equal class prior probabilities, probability of omega 1 and omega 0 are equal. So, both will be half. So, we can simply put probability of omega 0 equal to half dx. Now, for the next term 0.25 to infinity. So, 0.25 is your value of a. From 0.25 to infinity, you will have to compute the class conditional density of class omega 1. So, the class conditional density of class omega 1 is defined from minus a to a. So, if your a is 0.25, so it is not defined after 0.25, I mean it is 0 after 0.25. So, the next term does reduces to 0, because your probability x given omega 1 is 0 for the region x greater than 0.25. So, you are simply left with this particular expression. So, you can simplify this expression to get so the final value that we will get is 1 minus e to the power minus 0.25, half of this. So, this is the final probability of error. So, this was the problems for today. If you have any questions, you can you can ask at this point. This session I will be there for till 6. I will not do any more problems. If you have no questions, you can drop off at this point, but if you have any questions, we can discuss that. I will be available here till 6. Pranshul, please go ahead. usual, I have see that you have raised your hand. So if you have any doubts, you can please unmute and ask. Otherwise, you can lower your hand. So Sandeep is asking, ma'am, these questions are based on week 2 syllabus. No, these are based on week 1, which is the base minimum error classifier and base minimum risk classifier. So I am just doing some special cases where you are given the probability densities, conditional densities. Yeah, some of these can again come up in the next week. But the main idea is on the base minimum risk classifier, base minimum error classifier. Shashi is asking what math prerequisite this course has. I guess you should have basic knowledge of linear algebra and some calculus. Some basic knowledge only will be sufficient. Yes, we are going to provide the links of these sessions as recorded ones. So you will get both the slides as well as the recorded video links. Yeah, thank you everyone for joining. Mani, ma'am, can we get similar kind of solved examples for reference? So we will be solving these problems over here only. You will get these. You can go through different books to get similar examples. What is the schedule for tomorrow's problem solving session? Safik, I don't think there is a problem solving session for this course tomorrow. I guess the sessions are on Saturday and Tuesday. You can check it in the course web page. The timings will be given. I guess two more TAs will be taking this type of problem solving sessions, but both of those sessions will be on Tuesday.
Yeah, Tanuka, one more question from my end. Like on Tuesday, as you said that we'll be having session on Tuesday. So what time it would be?
I am not sure exactly. Can you please check in the announcement page of the website? It's
Okay, no
already put
problem.
up there. That I know.
No problem. No problem. I'll check there.
Yeah, you'll also get mail notifications. I guess you got today, right? Some mail notification.
Yeah, I got today, so that's what. But it was not mentioned regarding Tuesday, so I thought to
Ah,
just check.
okay. You can just check over there. Otherwise, you will also get these mails on that day.
Okay, great. Yeah, thanks.
Yeah. Sashi, do you know who is going to take the other session? Okay, some more PMRF TAs from other institutes will be taking this. Ma'am, it's it's little difficult to understand the deep learning maths. Is there any steps to understand it easily? Okay, I mean, there is no such steps. You should get your basic linear algebra and this probability and what do you say, integration clear. So once you have clear idea of probability basics, linear algebra basics, it should be good to go. You should attend this session one by one, go through each of the problems that will be solving for you, and if you have any difficulty at any step, you can come to us and we'll be happy to solve that. Yeah, I guess only solving more problems is the key to understanding. Hey madam, good textbooks for deep learning. For these basic things like these Bayes classifier and these stuff, you can go through the Bishop's pattern recognition book. That is a very classic book for machine learning. And for deep learning, we have the Goodfellow's book, which is the most authentic, most original book of this, but that's a bit difficult to go through, I'd say. Will this course going to cover practical aspects of this as well, like Python? No, Sashi, we are not going to do any Python implementation of networks. With this will be only the theoretical aspect will get. Can you please share the textbook name? Okay. Okay, I need to look up the name. Just a minute. Let me see. Deep learning. Other one is this. This is for Penelope PS. I have shared the textbook names for both. One is deep learning and other is machine learning book. Can I ask my queries related to deep learning in future session if time permits? Sure, Shashi. Every Saturday we will have 2 hour session. Mostly the first 1 to 1.5 hour I will be solving problems, and the remaining half an hour you can ask the doubts you have. I'm asking about doubts related to deep learning but not covered in the course. Okay, so yeah, if it's possible to answer, I'll be happy to answer. But if it goes too far beyond the course, so that will not be a good idea to discuss for the others. So they'll not get the idea. But as long as possible, I'll try to explain the doubts. Ma'am, as I saw in announcement portal, there will be 3 sessions in a week, right? That is on Saturday 4 to 6, Monday 6 to 8 and 7. So in all the session, question will be different or same, and it is necessary to attend all the sessions so that we don't miss out on any. But so Pranshul, the idea is mostly these same topics will be covered on in all the TA sessions. So like today I did problems on mostly week 1 and I guess a few aspects of week 2 maybe. So the other two TAs will also be doing doing the same syllabus and same topics in the same week, but the exact problems, mostly the problems will also be similar, not exactly same but similar, but yeah, some bit difference will be there from TA to TA, but mostly the topics will be same. You can, if you have time, you can of course attend all the sessions. There might be some questions that I am not discussing that they might discuss, but mostly we will try, each of us will try to cover the entire aspect. I am asking the same question because I got disconnected when I asked. Oh, no problem, sure. Yeah, so the idea of doing these 3 sessions were that this course has a lot of registered students, so it's not possible for everyone to join at the same timing. So to adjust everyone, we have given 3 sessions. Mostly we'll try to cover same topics also, but yeah, from TA to TA some difference will always be there. Though the topic is same, the questions might differ a bit. Are we going to cover hyperparameter tuning, regularization and optimization? I guess the syllabus is already put up in the course web page. You can go through the entire syllabus there. It was a good session. Thank you, Pranshul. If it helps, nothing better than that. Thank you, Sashi. Yesterday, Varshini, I don't think there was a TA session yesterday for this course. I mean problem solving session. Okay, link was sent. I'm not sure because this is my first session as far as I can tell you. Atul, yes, we will also have these PPT links. These PPTs will be shared with you. Okay, so let us close this session for today. I hope all of your doubts were cleared and no more doubts are there for today. Thank you guys for joining. Let's meet again in the next week.